Hey everyone, let's answer a challenging multi-part problem. We're defining a transformation T from the set of 2 by 2 matrices to the set of 2 by 2 matrices, right? So the domain and codomain are both the set of 2 by 2 matrices. And the way the transformation works is it maps a matrix A to itself plus its transpose. So remember that the transpose of a matrix means that you swap the elements over the main diagonal. So just recall that A, B, C, D transpose equals A, C, B, D, right? The B and C are the only things that switch, right? The A and D stay the same. Okay, so just put this off to the side here. Show T is a linear transformation. All right, so this requires 2 steps. First off, I don't know why that's talking all weird. There we go. T of, let's say, A plus B, right, 2 matrices, equals A plus B, right, we just plug that in wherever we see A plus B transpose. Now remember, we have to show that that's the same thing as T of A plus T of B. But that's not so bad, right, because we know that A plus B transpose is just A transpose plus B transpose. We showed this a few weeks back. So we can rewrite this as A plus B plus A transpose plus B transpose. Showed last month or last week, something. I think in section 2.1, that's what I'll say. Showed in, I think it was section 2.1 or maybe 2.2. It was one of them. Right, just to be clear, crystal clear here. This is the same as this, and we showed it there, okay? And then how is this helpful? Well, because we can rewrite this as A plus A transpose plus B transpose. And that's, of course, the same thing as T of A plus T of B. So you see how we did that? We showed that T of A plus B equals T of A plus T of B. So T satisfies that first linear criterion. Now the next part is we show that T of C times A equals C times T of A. Well, this is going to give us CA plus CA transpose, like that, right? We're just plugging in CA for A, right? So we do that, well, CA is going to be CA. It turns out, I think you can see this, but if you multiply multiply a matrix by a constant, by a scalar, and then transpose it, that doesn't matter whether you multiply it by the scalar first or after you transpose. This is going to be just the same thing as C times A transpose, right? You can factor out the C whenever, right? And then at that point, we can factor out C times A plus A transpose, and then that's, of course, the same thing as C times T of A. So these two conditions show that T is linear. Okay, if I had some more space, I'd write so T is linear, but I ran out of space. All right, now, by the way, there's a little bit of I think a misstatement on my part. Let B be any element in the codomain. Please write the word co there, right? Such that B equals B transpose. Find an A in the domain such that T of A equals B. Okay, so B equals B transpose means that I should say implies, or maybe is equivalent to saying that, let's say, A, B, C, D equals A, C, B, D. Do you see that, right? Because, right, from up here, right, they have to be the same thing. So A equals A, D equals D, that's fine, but note that that means B has to equal C. Okay? So that's what we're looking for. A matrix whose entries here are both the same thing. So let's say, given a matrix B, which equals A, B, actually, I'll call this C, 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 D, right? Because we said that these two entries had to be the same, right? So I'll call them the same thing. We want to find a matrix A such that T of A equals A, C, C, D. Okay? That's what we're trying to do. So let's just think for a second. What matrix A could we plug in to give us that? Well, if you think about it, this just requires a little bit of cleverness. And stop the video if you want to think about it. But I think this is going to work. Let A equal 1/2 A, 1/2 C, 1/2 C, 1/2 D. Or if you prefer to write it this way, you can write it like this. 1/2 A, C, C, D. Right? So T of A is going to equal, right, T of 1/2 times that matrix, right? That's going to be, what will that give us? 1/2 A, C, C, D plus its transpose, which is actually just itself. I'll write that down. I'll say, it's A, C, C, D transpose. Oh, whoop, no, hold on one sec. Transpose, right? But again, as we said before, the scalar, it doesn't really matter if you transpose the scalar, right? That's still going to be 1/2 A, C, C, D plus, and also note that it equals its own transpose anyway, right? A, C, C, D, right? And that just winds up equaling A, C, C, D. All right, so there we go. We did it. We found a matrix A such that T of A equals B. You might even just write equals B. Awesome. Now, we want to show that, in fact, the range of T is all matrices of this type. They're all, no matter what matrix A we plug in, we're always going to get a matrix of this form. So let's just take a generic matrix, A, right? Let A equal A, B, C, D, right? That's just a generic 2x2 matrix. So T of A, B, C, D, what's that going to equal? It's going to be A, B, C, D plus A, B, C, D transpose. And then that equals A, B, C, D plus A, C, B, D, right? Because we just transposed it, right? And that, if you think about it, let me just make sure we separate this problem from that. Okay, right, I'm going to write it down. Yeah, okay. So we're going to get 2A, B plus C, C plus B, which is just the same as B plus C, 2D. And do we see that that equals its own transpose because the non-main diagonal entries are the same? Right? So we have that. Okay? Right? So just to be clear, maybe this isn't a complete proof, but so the range of T is the set of T of A, which, just equal, I should say, which is the set of all, I'll just erase that. 2A, B plus C, 2D, for A, B, C, D in the reals. Okay? So we're done. Right? Because that equals its own transpose. So no matter what you plug into the transformation T, you're always going to get a 2 by 2 matrix that equals its own transpose. Now, using that information, we're going to find the kernel of T. Okay? Now, it was very helpful that they asked us part 3 before part 4, because now we know what to expect from T, right? We know the output. So we'll say, since we know that T of A, B, C, D equals, let's do that, equals, what's that going to be? 2A, B plus C, B plus C to D, we want that to equal 0, right? I'll say which we want to be the 0 matrix, right? Because we're trying to find the kernel of T. We need the following things to happen. We need 2A to equal 0. Oh, I guess we also need 2D to equal 0. Right, so we have A equals D equals 0. And we also need B plus C to equal 0. And so I'll say C equals negative B. Maybe I'll just say B equals negative C, just because we've been using C as the variable, right? Okay? So the kernel of T equals the set of all matrices 0, negative C, C, 0 for real numbers C. You see that? Right? Because just try it, right? Plug in any matrix of this form into T. And you're going to get the 0 matrix, right? Right? It's itself plus its transpose, right? The C and the negative C flip. You get 0. Furthermore, we've also shown, containment the other way, right? Because the only way you're going to get the 0 matrix is if these two entries are 0 and these two entries are, their own negatives, right? So it has to be perfect equality. All right? So that's the proof.